Hi, welcome again to Advanced PLCs. My name is Paul, in case you forgot. And today I want to talk a little bit about background of controls. So this is before we get into actually programming the PLCs. I want to talk about what we do with PLCs and why we need PLCs. Let's look at what we got going on in Canvas. Here we are on the home page of Canvas, and I want to go to Unit 1. I'll click on that guy. And then under Resources for Section 1, I'll click there. It's this first guy. It's called Murray Mini Lecture. So that's the slides that I'm going to be talking about, and I'll also have this video linked on Canvas. This is an introduction to industrial automation. First thing is, how can computers talk to a machine? There's all sorts of new and interesting things going on in the world. We've got self-driving cars, we've got Internet of Things where your washing machine can talk to your fridge, and we've got artificial intelligence. So a lot of neat stuff going on in computers and in technology. But what I want to do is take a step back and talk about how do computers actually talk to the machines. How does it work? Here I've got an example. I show a laptop and I show a water valve. How can a laptop make a water valve go on and off? Well, with this type of valve it can't. So let's look at what we need to do a water valve, to move a water valve. First, we need energy. Something needs to actually physically move that valve, whether it's a hand valve or a motorized valve. And so we could hook a compressor up to a motorized valve. That would give the energy to move that valve. But we still can't talk to that valve because the laptop just can't talk to a valve directly. Alright, so we put a control valve in the middle. The control valve will turn the energy on and off. That works, and that would let us move that big valve. But we still can't talk to the control valve. We need a PLC, a programmable logic controller. The PLC can talk to the laptop, and the PLC can talk to that control valve. It can send a signal out. For outputs, we've got two kinds that we deal with. One is digital, and that's on-off. It's also called discrete. And the other is analog, and analog is variable. For inputs, we've got three kinds. We've got digital, same as with analog. For inputs, we've got three kinds. We've got digital, we've got analog, which is variable, and then we have a special one called thermocouple inputs. And we don't really use thermocouple inputs in the lab, but it's good to know that there is a separate special type of input. Alright, so here's our working solution. We've got our laptop talking to the PLC. The PLC sends signals out to the control valve. The control valve is getting its energy from some energy source. In this case it's a small compressor, but could be any source of energy. And that control valve sends the energy to the water valve and actually makes it move. And I think in this case maybe it's a spring return. So you send energy to the valve, it makes the valve open. When you remove that energy, the spring will make the valve close. Alright, so there's two kinds of inputs needed to make that valve move. What are they? And if both of those inputs are there and the valve doesn't open, what causes it? And how do we know? So give that some thought, and we're going to have a discussion on that coming up. So we need two things to make the valve move. We need our information, we need the signal, something to tell it to move, and we need a source of energy that can physically move it. If you don't have, or if you do have both of those and the valve doesn't move, then what's going on? And guess what? It's maybe the valve is broken. How do we know if the valve moved or not then? What sort of confirmation do we have? There's three kinds of confirmation that we could have. First is no confirmation. If you think of a water sprinkler system at someone's house, we don't have any confirmation directly from those sprinkler valves that they opened. The controller sends a signal to the valve and we presume that the valve is going to open. There's other feedback, such as if the grass is dying, we know the valve's not working. Or if the grass is not wet when you think it should be wet, you know the valve is not working. It's easy, and for low consequential activities, such as watering your grass, we don't really need feedback. The second kind of feedback is we have a valve self-confirm that it's opened. We might put a switch on top of the valve, and the switch is activated when the valve moves. So in this case of this controller, when we send the signal to the controller, this little guy on top is actually a rotary indicator, and we could put a little limit switch on there and send a signal back to the PLC to tell the PLC that that valve moved. That's a pretty good type of feedback. You send a signal to the valve to tell it to move, and then you get a signal coming back to say that it did move. But let's look closely at this valve. If we send our signal to these connectors at the top, and we put our little limit switch right there at the top, the valve is going to tell us when it's moved. But a couple other things could happen with this valve. This connector in the center could be broken. The valve itself could be damaged or stuck. So we might get a false signal that this valve is telling us that it moved, but it might not actually be open. And third kind of signal, or third kind of feedback, is independent confirmation. Instead of having this valve tell us that it opened, we could actually put a flow switch downstream from this valve to actually measure whether or not the water or whatever the fluid is coming through the pipe. That would be an independent confirmation. Now, independent confirmation is the most reliable because it's independent, but it's also the most complex, requires the most maintenance, and it's the most expensive. Whenever you design a control system, you have to decide how much feedback do I need? Do I need any? And what's it going to cost? Here's an example of a feedback system. In this example, we're filling a tank with water, and we have a level switch that tells us when the tank is full. So that's an independent feedback. In summary, computers and PLCs communicate. PLCs issue commands, that's our PLC outputs, and the machine somehow sends a signal back to say that it's done the command. That's our PLC inputs. And then the PLC conveys information back to the computer. So in that way, computers actually can talk to machines. Here's some things to think about. First of all, are PLCs still relevant? PLCs have been around for a long time. They're introduced 50 years ago. It's a long time, especially when you consider that smartphones have been around since mid-2000s. So smartphones have been around for like 15 years, and PLCs have been around for 50 years. PC computers have been around since the 70s or 80s. So they've been around for 30 or so years. Are PLCs still relevant? And if they're not, what out there is going to replace it? And an interesting thing about PLCs is the ControlLogix is the latest and greatest PLC. It came out in the 1990s. So this PLC is 30-year-old technology. 30 years old, and it's the latest and greatest. It's on a very different time frame for development compared to smartphones and computers. And we'll talk more about that in the future. Next question is other ways a computer can talk to a PLC. We've got HMIs, we've got wireless communication. How are PLCs programmed? Is there only one way to do it, or are there many ways to do it? And what are the external influences that affect PLCs? Are there political, social, environmental influences, or are these things kind of on their own and not affected? And lastly, can you build your own PLC? And the answer to that is yes, you can, and if you're interested, we can work on that during the semester. Alright, thanks for listening. That's the introduction to controls. Talk to you soon.